Hello, dear students. In the previous lecture, we talked about this example, which is applying the cylindrical coordinates in solving triple integrals. Here, we use the cylindrical coordinates for finding the volume, which is bounded by this function and this one, and also z equals 0. We solved that example in the previous lecture. We now have another example. It says evaluate this triple integral by changing it to cylindrical coordinates. That means here, this is the Cartesian coordinates. We must convert it to cylindrical coordinates, then find the triple integrals. Now, let's write down the function below, the triple integral below. This is 2. The integration from 0 to 2, integration from 0 square root of 4 minus x squared, then the integration from 0 to, sorry, it's from x squared plus y squared to 4 for x squared dz dy dx. For x squared dz dy dx. Here we said in cylindrical coordinates r equals the square root of, or let's say r squared equals x squared plus y squared. X is r sine theta, so r cosine theta. Y equals r sine theta. Okay, we have this. We do these changings here. That means we must have no x and y in the triple integrals. We must convert to cylindrical coordinates. That and in the cylindrical coordinates, it's possible to have z, theta, and r, and no more variables. Here, we have x squared y squared. Z equals x squared y squared to 4. 4 is constant. We don't care about that, and it's okay to be 4. But here, we have z equals x squared plus y squared. In this case, we can say z equals r. That means z belongs to r. Here, you see z equals x squared plus y squared. So z equals r squared. That means z belongs to r squared to 4. As you see, the upper limit is 4. We don't change because there's no x and y terms in the upper limit. But in the lower limit, we have x squared plus y squared. By applying this rule, we can say it is r squared. And in the second one, we draw the graph of y. We say y equals square root of 4 minus x squared. And the graph of this function is y, this x and that's y. It's between x and y. Here, it's from 2 to minus 2. This is a semicircle. This is the upper part of the circle. Here we can find both r and theta. From the graph, you can see that the radius here is 2. From anywhere, I mean the distance from the distance of the origin to any point on the boundary is 2 units. That means here y becomes, I mean y belongs to 0. Yeah, we have r actually. Actually, it's r. R belongs to 0 to 1. That means the length of r is from 0 to 2. Sorry, not 2. as from 0 to 2 because the radius is 2. As you see here, the distance from here to here is 2 units. So starting from the origin means from 0 to 2. So r belongs to 0 to 2. And then we have theta. Theta is starting from here to here. Here's 0, here's pi. That means theta belongs to 0 to pi. Now we have the lower and upper limits for each z, r, and theta. So you can write down the triple integral in cylindrical coordinate form. But here you have x squared, and you say x squared equals r squared cosine squared of theta. Because we said x is r cosine theta. We now look, we took these rules from here. These are the rules which are given before, and we talked about those rules during the last lecture. Now we say the triple integral becomes the triple integral for x squared becomes r squared cosine squared of theta. Then we replace dz dy dx by r dz dr d theta. Always dy dx equals to r dr d theta. Okay, and dz is itself. Here, for the first integration is with respect to z. That means z is from r squared to 4. We found it here before. And the second is with respect to r. R is from 0 to 2. And the third one is with respect to theta. Theta is from 0 to pi. Now we are trying to find this triple integral. It equals to the first you take the integration with respect to z. Okay, we take the integration with respect to z. Say it's the double integral from 0 to pi and from 0 to 2 for integration of this one. Here we have r times r squared. R and r squared becomes r to the power 3 or r cubed. The integration of r cubed cosine squared of theta. Here we have no z in this term. That means it's constant regarding the integration. So taking the integration with respect to z, is z times, we just multiply the constant by z. It's a constant if we take the integration with respect to z, because here we have no z, so it's a constant. Z r cubed cosine squared theta from r squared to 4. From r squared to 4. Now replace z by 4, then replace z by r squared. We have dr d theta. Dr d theta. Now it equals to the integration from 0 to pi, and the other one is from 0 to 2. For z, here we first replace it by 4, which is 4r cubed cosine squared of theta minus, then we replace it by r squared. R squared times r cubed is r to the power 5 cosine squared theta. This is the result of the first integration. Now we have two more integrations. First with respect to r and the second with respect to theta. The integration of this function with respect to r equals to the integration from 0 to pi. This is pi, sorry. From 0 to pi, integration of this function with respect to r. The integration of this function with respect to r is 4r to the power 4 divided by 4, and we get r to the power 4. Okay, we get only r to the power 4 cosine theta minus r to the power 5. Its integration is r to the power 6 divided by 6 cosine squared of theta. And here, r is from 0 to 2. It's from 0 to 2. And you say it equals the integration from 0 to pi. We first replace r by 2, then you replace by 0. When you replace r by 0, both terms become 0. But here we just replace r by 2. This, if you replace r by 2 here, we get r to the power 4. And r to the power 4 is 2 to the power 4 is 16. 16 cosine theta. This is squared, sorry. 16 cosine theta minus r to the power 6, which is 2 to the power 6. 2 to the power 6 is 64. Dividing by 6. Cosine squared of theta. Minus 0. O d theta. Okay? Because when you replace r by 0, you get 0. Now we simplify this. We have 16 cosine theta minus 64 over 6 cosine. Both are cosine squared, sorry. We have 16 cosine squared of theta minus 64 over 6 cosine squared of theta equals to, we just find the sum of these two. Okay, first let's simplify this. Dividing by 2 is 3, and dividing by 2 is 32. That means it's 32 over 3. Okay. Now we find the common denominator between these two. We have 16 cosine theta minus 32 over 3 cosine squared of theta. This the integration from 0 to pi for 48 cosine squared of theta minus 32 cosine squared of theta dividing by 3 all d theta, and this equals to 48 minus 32 is 16. 16 cosine squared of theta dividing by 3, the integration from 0 to pi for d theta. Now we take integration for this function with respect to theta, but here you have cosine squared. You have cosine squared, and we have these rules for converting it. This rule, the second one, cosine squared of x equals 1 plus cosine 2x over 2. We apply this rule to simplify cosine squared of theta. So cosine squared of theta becomes 1 plus cosine 2 theta over 2. Here we say it equals to integration from 0 to pi for 1 over 2. So let me write down 16 over 3 first. We have 16 over 3. It's a half plus a half of cosine 2 theta. Then d theta. Now we multiply 16 over 3 into the brackets, into this and this one. We get integration from 0 to pi for 16 over 6 plus 16 over 6 cosine 2 theta. Okay, and here 16 over 6 could be cancelled out. This dividing by 2 is 3, dividing by 2 is 8, and dividing by 2 is 3, dividing by 2 is 8. That means it becomes 8 over 3 for both. 8 over 3 and 8 over 3. Then d theta. We can now find the integration. It's easy to find the integration of cosine 2 theta. We must first have the integration of the angle, which is 2. So we give 2 for this one and dividing it by 2. That means it becomes, let me write down it, 8 over 3 times 2 times a half. The integration of 8 over 3 with respect to theta equals to integration of a constant with respect to theta is the constant times theta. So it's 8 over 3 theta plus. Here we have 1.5 multiplying by 8 over 3, which is, yeah, these will cancel out. It's 1 and it's 4. We get 4 over 3. And we have integration of 2 cosine 2 theta. We have the derivative of the angle, which is 2. That means its integration is sine 2 theta. Where theta is from 0 to pi. When you replace by pi, the first term becomes 8 pi over 3 plus the second term. Here we get sine 2 pi, which is 0, minus. When you replace by 0, the first one is 0 and the second is 0. It equals 8 pi over 3. That means this is the result for that example. That's the result for that triple integral. Okay, it's so easy. It's, here the most important thing here is how to find the upper and lower limits for the integrations. That's all. After finding this, the others is only taking 3 integrals. It's so easy. And the third one, we have another example. It says evaluate the triple integral of z over the square root of x squared plus y squared dv, where g is a solid bounded by the plane z equals 2 and the surface z equals x squared plus y squared. First, let's write down the given things below. This is the third one. I'm going to write down the given things here. It says the triple integral of z over x squared y squared in squared. It's triple integral over g for z over squared root x squared plus y squared in a squared dv, which is bounded by z equals 2 and z equals x squared plus y squared. Z equals to, sorry, z equals to z equals x squared plus y squared. It says the region is bounded by these two planes, these two functions. Here, first we should find the lower and upper limits for the function. We say, first let's draw the graph here. It's easier to find the, to find the lower and upper limits. Here, the graph of z equals x squared plus y squared. It is a parabola. It's like this. Okay. It says the region is bounded by this graph, this function, and z equals 2. At z equals 2 here, we have a plane. We have a plane. That means here the region which is bounded by these two is only this. This is the region. This is the solid which is bounded by the plane z equals 2 and that paraboloid. We now have the lower and upper limits for z. Z is starting from this function. That means it is from x squared plus y squared to what? To 2. Here, x squared plus y squared is r squared. That means the lower and upper limits for z, let's first write down the 3 integrals, and the triple integrals. Z is from r squared to 2. It's dz. Now, we are going to find the lower and upper limits for r and theta. It says z equals 2 and z equals x squared plus y squared. That means x squared plus y squared equals 2. Since z equals 2, so we can say this. This is a circle of radius square root of 2. Is it? This is r squared. So r is 2. That means, as you see, it's a circle of radius square root of 2. That means r is from 0 to square root of 2. R is from 0 to square root of 2 from all sides. Okay, from 0 to square root of 2. And then for finding theta, as you see here, this goes from 0 to 2 pi, from 0 to 2 pi. So the third integral is from 0 to 2 pi. dz, dr, d theta. But here we must multiply it by r because dx dy is r dr d theta. Here we have r already. Now we have the function. We have a given function here. The given function is z over square root of x squared plus y squared. As I said before, it's possible to have z in the function, but we must have no x and y in the function. And we said r squared equals x squared plus y squared. So r is square root of x squared plus y squared. That means here we replace x squared plus y squared by r. We replace this by r, and it equals z over r dr d theta. These are cancel out. That means we just get z here. Z dz dr d theta. Just find these triple integrals, first with respect to z, second with respect to r, and third with respect to theta, and write down the result. It's so easy. Let's do it. First, with respect to z, to find the integration of z with respect to z is z squared over 2. That means equals this double integral from 0 to 2 pi, from 0 to square root of 2, since we took the first integration. So we have two integrals left. Z squared over 2 from r squared to 2 dr d theta. It equals the double integration from 0 to 2 pi, from 0 to square root of 2. Here we first replace it by 2, then we replace by r squared. I get 2 minus r to the power 4 over 2. Here we get this. When we replace by 2, it's 2 squared was 4. 4 divided by 2 is 2. Then minus, if replaced by r squared, it's squared also, becomes r to the power 4 over 2. Then this is dr d theta. Now we take an integration with respect to r. The integration of 2 minus r to the power 4 over 2 with respect to r is 2r minus r to the power 5 dividing by 5. And you have 2 also, it's 10. From 0 to square root of 2. Now we replace r by square root of 2 first, then by 0. When you replace by 0, both terms become 0 because in both terms you have r. This is d theta. We have only one more integration. But first, let's replace the lower and upper limits to the function here. First, we replace r by square root of 2, and we get from 0 to 2 pi. For 2 times square root of 2 minus r to the power 5 means square root of 2 to the power 5 over 10. Minus, if we replace r by 0, we get 0. All d theta. Okay, now it equals to the integration from 0 to 2 pi. 2 square root of 2 minus square root of 2 to the power 5 is square root of 32. Because it's square root of 2 to the power 5 is 32. And it is 16 multiplying by 2. This is 16 multiplying by 2. 16 is 4 square root of 2 dividing by 10. Now we can find the sum of these two. We can simplify this. It becomes from 0 to 2 pi. Finding the common denominator here, we get 20 square root of 2 minus 4 square root of 2, 16 square root of 2 dividing by 10. d theta. Now these two can be cancelled out, dividing by 2. This is 5, this is 8. So you get 8 square root of 2 dividing by 5. And here we find the integration with this, I mean with respect to theta for that function. It equals to 8 square root of 2 over 5 theta from 0 to 2 pi. And equals to, first we replace by 2 pi, then we replace by 0. When we replace by 0, we get 0, but when we replace by 2 pi, we get 16 pi square root of 2 dividing by 5. So this is the result. This is the result of that triple integral. That's it. For the third one, the result is 16 pi square root of 2 over 5. We now have another type of, another type of triple integrals, which is triple integrals in spherical coordinates. Up to now, we talked about triple integrals in Cartesian coordinates, triple integrals in cylindrical coordinates, and now we have triple integrals in spherical coordinates. For the triple integrals in spherical coordinates, we replace each x by rho. This read as rho, it's not p. Okay. Rho sine phi cosine theta. Y equals rho sine phi sine theta. And also z equals rho cosine phi. Z equals rho cosine phi. And we replace x squared plus y squared plus z squared by rho squared. We say rho squared equals x squared plus y squared plus z squared. Here, phi is always from 0 to pi. That means phi must not be greater than pi and less than 0. And also, theta is from 0 to 2 pi. It must not be greater than 2 pi and it must not be less than pi. Okay? We just do these modifications in the example, then finding it with respect to, in the spherical coordinates. Here we say the triple integral, the volume, this dv, which is the volume. The volume of the solid, which is bounded by G in the region G, equals to rho squared sine phi. If you remember, in these cylindrical coordinates, we said when we change dx dy to dr d theta, we always say it's r dr d theta. We multiply it by r. But here in spherical coordinates, we multiply it by rho square sine theta. We always write down rho square sine theta. Even if you have a function, for example here, even in this example, when we change this to d rho d phi d theta, we say we should multiply the function by rho squared sine theta, sine phi, sorry, multiplied by rho squared sine phi, then d rho d phi d theta. Okay, so this is the rule for finding the volume of a solid bounded by G. Here we say the triple integral of f of rho phi theta dv equals rho squared sine theta, sine phi, sorry, as you see, d rho d phi d theta. We have some examples. We now solve them. We now have some examples about using the spherical coordinates. Here, the first one, it says, use the spherical coordinates to find volume of the solid G, bound above by this sphere. It's bound above by that sphere and bound below by this cone. Let's first write down the equations here. X squared plus y squared plus z squared equals 16. For the first one, it's x squared plus y squared plus z squared equals 16. And also, it says z equals square root of x squared plus y squared. Okay, now here we should find the volume of the solid which is bounded above by this sphere and bounded below by this cone. First, let's draw the graphs. The graph of the first one, I mean for the sphere, we're going to draw both together on the same XYZ planes. That's X, that's Y, and Z. For the first one, it is a sphere. It is a sphere. It's like this. Okay, this is a sphere. And Z equals x squared plus y squared. It's a cone. It's a cone like this. It's a cone on the Z plane, on the Z axis. Yeah. So the volume was bounded by these two, I mean bounded above by the sphere and bounded below by the cone as this solid. So you should find the volume for that solid. To find it, here we should find the limits for the integration. The limits for the integration is here we have triple integrals for d rho, d phi, d theta. Let's see how to find rho, phi, and theta. I mean the limits for rho, phi, and theta. I'm going to show you this figure. This is the graph for the function. I mean, this is the graph for the solid. Here, we should find the volume for this solid. To find the volume for the solid, we say we should have rho. We should have rho, the limits for the rho, and the limits for phi, and the limits for theta. For rho is the distance. For rho, we say it is the distance from the origin. It's from the origin to the. It's from the origin to the boundaries. Okay. So this distance is, as you see here, the distance. So the distance from 0 to the boundary of the sphere is 4 units, because it says x squared plus y squared plus z squared equals 16. That means this is r squared. Okay, what's rho squared? It's rho squared. And rho is 4. That means rho is starting from 0 to 4. Then we are going to find phi. To find phi, we always, we always have angles for phi and theta. I mean, phi and theta are angles. For phi, we count the angle from this to here, up to here. Okay. So what's the angle here? The angle here is from here to here. Okay, because this is the cone. This is the cone. Our solid is bounded by this part of the sphere and the cone here. So this angle, we don't need to expand the angle to here, because this area is not belong to the solid. And this angle, it is exactly between y and z. It's exactly between y and z. And from here to here is pi over 2. That means from here to here, this is pi over 4. This pi over 4. This angle is pi over 4. If we count it from Z, at Z, the angle is 0. Up to here, it's pi over 4. That means phi is from 0 to pi over 4. Then for theta, we say the rounded one, the horizontal angle. As you see, we have the cone like this. It's going from here to here. That means it's from 0 to 2 pi. As you see, it's from here to here. It returns to the same place. Look, it is from here to here. That means the angle for theta is from 0 to 2 pi. Let me show you on the graph here. It says the value of phi, sorry, this is the graph. For phi is from the z-axis to that end, to that line, to the boundary of the cone. This angle is 45. That means from 0 to 45. 45 is pi over 4. Okay, that means phi is from 0 to pi over 4. And theta is the rounded one. Look, it's from there to there. That means it is 360 degrees, which is 2 pi. That means phi is from 0 to pi over 4, and theta is from 0 to 2 pi. But here, as I said before, we must all multiply it by r squared, so rho squared sine phi. Now, we are going to find this 3.2. So the most important thing here is to find rho, phi, and theta. I mean the limits for rho, phi, and theta. Okay, here we found rho. Rho is the radius of the sphere, which is 4, from 0 to 4. And for phi, starting from this line at z-axis, the angle is 0, up to pi over 4. And for theta is from here to here, which is 2 pi. Now, we have all the limits, and we have the function also as rho squared sine phi. As I said, in the cylindrical coordinates, we multiplied by r, but here we multiplied by rho squared sine phi. Now we take the integration for the function with respect to rho. Here we have rho squared sine phi. Sine phi here is a constant, and the integration of rho squared is rho to the power 3 over 3. It equals to the integration from 0 to 2 pi. We take the first integration with respect to rho, and then the second integration with respect to phi is from 0 to 4, and it is rho cubed over 3 sine phi from 0 to 4. From 0 to 4, d phi d theta. Now we replace first rho by 4 and then by 0. When we replace by 0, it's 0. So you get 4 to the power 3 over 3 sine phi. It equals to the double integration from 0 to 2 pi and from 0 to pi over 4. For 4 cubed is 64 over 3 sine phi. D phi d theta. Now we take and the integration with respect to phi. If we take the integration for this function with respect to phi, we have sine phi. The integration of sine is minus cosine. It becomes the integration from 0 to 2 pi cos 64 over 3 cosine phi, and you have a negative sign also, because integration of sine is minus cosine. Then d theta. But here we have the lower and upper limits for phi, which is from 0 to pi over 4. Now we replace phi by pi over 4, then minus we replace by 0. It equals the integration from 0 to 2 pi for minus 64 over 3 cosine pi over 4 minus cosine 0 d theta, and it equals to the integration from 0 to 2 pi cosine pi over 4 is square root of 2 over 2, which is 1 over square root of 2. It's minus 64 over 3, 1 over square root of 2, minus cosine 0 is 1, d theta, sorry. It equals to the integration. We simplify it more from 0 to 2 pi. Here we multiply this minus 64 over 3 into the bracket. We get minus 64 over 3 square root of 2 minus times minus is plus 64 over 3 all d theta. Now we take another integration with respect to theta. It equals to minus 64 over 3 square root of 2 theta. When we take integration with respect to theta, these are constants. We just multiply them by theta plus 64 over 3 phi from 0 to 2 pi. You first replace theta by 2 pi, and then you replace by 0. When you replace by 0, you get 0, and it equals to minus 64 over 3 square root of 2 plus 64 over 3, all multiplying by 2 pi. Okay, this is the result for that example, and you can simplify it more by finding the common denominator here. This is the result for the first example. We now have another example. In example 2, it says use spherical coordinates to evaluate this triple integral. The triple integral is given on the Cartesian coordinates form. Now we first should convert this Cartesian form to spherical form. I've written down the example here. In these spherical coordinates, we have these rules. We say x equals rho sine phi cosine theta. X equals rho sine phi cosine theta. And also y equals rho sine phi sine theta. And you also have that z equals rho cosine theta phi. Okay, and you have x squared plus y squared plus z squared equals rho squared. Okay, we use these rules here. First, let us draw the graph of this region, okay, of the solid. Here z is from 0 to the square root of 4 minus x squared minus y squared. You say z equals square root of 4 minus x squared minus y squared. This is a semi-sphere. It's a semi-sphere. It's like this. Yeah. This is x-axis, that's y-axis, and the z-axis. This is a semisphere. Its radius is 1. Its radius is 2. Sorry, its radius is 2. Okay. Now you have also that y equals plus minus square root of 4 minus x squared. This is equation of a circle with radius 2. It is this. We have this also. That means here, what we do, we are gonna find this, the volume of this solid, or we are gonna find the triple integral to evaluate. We are gonna find the evaluation of the integral on this sphere. On this sphere, here we say it is from x from 0 to 2 over y-axis, and from z-axis from 0 to 2, and over x-axis also from x to 2. Okay, and now we should find the limits for rho, for phi, and for theta also. For rho, as you see here, it's starting from the origin. From the origin to the boundary of this solid is 2 units. It's the radius. From anywhere, if we go onto the boundary, yeah, we get 2. That means rho belongs to 0 to 2. So it means rho is from 0 to 2. And then for finding phi and theta, we say phi, for finding phi, we always start from this line. I mean, from the z-axis. We start from here up to here. Why? Because the solid is, we have the solid in this area. We don't go to down here because the solid is not in the down of the y-axis. That means the values of phi, phi is from 0 to pi over 2. From this angle to this one, from this angle to this one is from 0 to pi over 2, because z is perpendicular to y-axis. That means phi belongs to 0 pi over 2. And x, as you see, it's going from here and returning to the same place. It's a circle. That means for theta, theta is starting from 0 to 2 pi. So theta belongs to 0 to 2 pi. As I said, 0 is the horizontal angle. That's the horizontal one. So the horizontal one is a circle. So for a circle, we say it is 360 degree, which is 2 pi. That means here we found all the limits for the integration with respect to x, with respect to rho, with respect to phi, and with respect to theta also. We found these 3. Now we are going to write down the triple integral on the spherical form. So we don't need this anymore because we found the limits. We have the triple integral first with respect to rho. We say d rho. First is with respect to rho. And rho is from 0 to 2. And the second is with respect to phi, d phi, where phi is from 0 to pi over 2. And we have d theta. Theta is from 0 to 2 pi. These are the limits. And now we have this function. We have this function. But before, as I said before, I said when we convert any Cartesian triple integrals to spherical coordinates, we should multiply it by rho square sine phi. Okay, we multiply by rho square sine phi, as we did in the cylindrical coordinates. We said we multiplied by r. Okay, we said dx dy or dy dx is r dr d theta. And here also it equals to rho square sine phi d rho d phi d theta. Dx dz dy dx equals to rho squared sine phi d rho d phi d theta. And here we have z squared times the square root of x squared plus y squared plus z squared. Here, x squared plus y squared plus z squared equals rho squared. How about the square root of this is the square root of the right hand side, and the square root of rho squared is rho. We have rho. And for z squared, we say z equals rho cosine phi. Z equals rho cosine phi. If we square it, it becomes rho squared cosine phi squared. Let me write down it again. Rho squared cosine phi squared times rho. Okay, this rho is for the square root. This is the square root of x squared plus y squared plus z squared, and this is z squared. Okay. We now write down again and simplify it. It equals to the integration from 0 to 2 pi, the integration from 0 to pi over 2, and the integration from 0 to 2. For rho squared, here we have rho squared times rho squared. These three is rho to the power 5. It's rho to the power 5. Now we have cosine squared of phi times sine phi. Cosine squared of phi times sine phi. D rho d phi d theta. We take the first integration with respect to rho. Here, cosine squared of phi times sine phi, this is a constant because we take the integration with respect to rho. Here we have rho to the power 5, and it equals to the integration from 0 to 2 pi. Integration from 0 to pi over 2. Integration of rho to the power 5 is rho to the power 6 dividing by 6. Now we have cosine phi, cosine squared of phi, sine phi. Where rho, we took the integration with respect to rho, and it's from 0 to 2. You have d phi d theta. And now we replace rho first by 2 and then by 0. When we replace by 0, we get 0. And when we replace by 2, it is we have the double integral from 0 to 2 pi and 0 to pi over 2. Rho to the power 6 means 2 to the power 6, which is 64. It's 64 dividing by 6. Cosine squared of phi sine phi d phi d theta. Here we can cancel out these two, dividing by 2 for both numerator and denominator. Numerator becomes 32 and denominator becomes 3. So we just write down 32 over 3. That's it. Here when we replace, we don't write down the other part, because when we replace rho by 2, we get that. And when we replace rho by 0, we get 0. That's why I haven't written down that part. And it equals to the integration. Here we take the integration with respect to phi. We take this integration with respect to phi. It's from 0 to 2 pi. We have cosine phi to the power 2 sine phi. Okay. We say if you have a bracket, let's say f of x to the power n times f prime of n of x, the integration of this is we just add the exponent by 1 dividing by the new exponent. So you get f of x to the power n plus 1 dividing by n plus 1. And here we have the similar function. We have cosine squared of phi times sine of phi. If we take its integration, the derivative of cosine is negative sine. So you must multiply it by negative, and you have a negative sign in the out of the integration. We have cosine squared of phi times negative sine of phi d phi. The integration is, here we have f of x, which is raised to the power 2, which is multiplied by the derivative of the function. It equals to, the integration is, here we have this negative sign, and cosine phi to the power 3 divided by 3. We get this. So the result, I mean, the result of the integration is minus 32 over 3 times cosine phi to the power 3 dividing by 3. Yeah, this negative sign is the sign which we got from the integration. It's from 0 to pi over 2. Okay. Then we the theta also. We first replace phi by pi over 2, then we replace by 0. When you replace by pi over 2, we get cosine of pi over 2. And cosine of pi over 2 is 0. That means the first part for the upper limit, we get 0. It's 0 minus. And then we replace by 0. Cosine of 0 is 1. 1 over 3 is 1/3, multiplying by minus 32 over 3. It is minus 32 over 3 times 1/3, which is minus 32 over 3 over 9. Is it? It is minus 32 over 9. This is d theta. We now simplify it more. It becomes the integration from 0 to 2 pi for 32 over 9 d theta. Now we take the integration with respect to theta. It becomes 32 over 9 theta, where theta is from 0 to 2 pi. And this equals to, we replace theta by 2 pi first, then by 0. When we replace by 2 pi, we get 64 pi over 9 minus. When we replace by 0, we get 0. So we have now this term. That means the result of the triple integral, the result of the triple integral is 64 pi over 9. As I said before in the previous example, the most important thing here is to know what are the limits for the integration. This is the most important part here. And after this, it's just taking integrations and it's just calculations. We have on the example 3, it's 2 parts. The first part, it says, use spherical coordinates to find the volume of the solid. Yeah, it's about finding the volume of the solid, which is bounded by the graphs of x squared plus y squared equals 4, and also z equals the square root of x squared plus y squared, and z equals 0. First, let's draw the graph. It's easier to find the lower and upper limits of the integration for the spherical coordinates. Okay. Let's write down the function. We say, it says the solid is bounded by x squared. It's 3i or a. I think it's a and b. Yeah, it's a. It's x squared plus y squared equals 4. And z equals the square root of x squared plus y squared. And also z equals 0. Let's draw the graph. For this one and this one, for the first one and for this one, it is it's a cylinder. It's a cylinder. here, the graph of x squared plus y squared equals 4. It is a circle with radius 4. And the graph of this function on the xyz plane, xyz plane, here, the graph is the circle. We have a circle. Now we expand the circle along y-axis, so it becomes a cylinder. We expand this along y-axis, z-axis, and it becomes a cylinder. Here we get this. Oh, sorry. Okay. This is the graph of x squared plus y squared equals 4 in R3. And the graph of z equals the square root of x squared plus y squared. This is a cone. This is a cone. This is one sheet cone. It is like this. Okay. This is the graph of z equals x squared plus y squared. And also z equals 0. Z equals 0. It is here. This line. And this one also. That means here we should find these two areas. This area, this one, the area was bounded by the cylinder, the cone, and z equals 0. It is here. Okay, this is the area or the region. It's the solid, which we should find the volume. Here we say the limits for rho, for phi and theta, we should find them all. Let's find them all. Okay, first for phi. Okay, for phi, for theta, and also for theta, for rho. First, let's find for theta. See theta, as you see, it's rounding. It's rounded. Okay, theta is from 0 to 2 pi. Theta belongs to 0 to 2 pi. This theta. And then for phi, as you see, this angle is 45. Let me draw it again here. Here we have this cone. Since the cone is z equals square root of x squared plus y squared, that means it's a right cone. So this angle is pi over 4. And the region or the solid is starting after this line up to here. It's starting from there to here. That means it's from pi over 4 to pi over 2. It's from pi over 4 to pi over 2. As you see here, it's starting from here to here. And at this line, theta, this theta is pi over 4. That means the angle of phi is from pi over 4 to pi over 2. Phi belongs to pi over 4 to pi over 2. This is for phi. And then for rho, we can find it from here. We can find rho from here, because as you see, if we draw the distance, look, let me draw the graph again. Here you have this, and you have this. From the origin, if we count, this is the cylinder, this is the cone, Okay, here we are going to find this and this area. I mean, here in front of here you have the solid also. From all sides, we have the solid. We say from the origin to here is different from the origin to here. It's different from the origin to here. Okay, it's different from the origin. It's different from the origin. It depends on the angle that we have. Look, for this one, we have 45. And here we have more. And here we have more. So it depends on the angle. Okay, finding rho, it depends on the angle. So here we cannot say rho is from 0 to a number. We are going to find rho. We say we have given that x squared plus y squared equals 4. X squared plus y squared equals 4. But we have that x equals rho sine phi cosine theta. And also y equals rho cosine phi, so it's sine phi sine theta. Now we square both. Let me check if I've written down the rule correctly. Yes, that's it. Now we replace x and y into here, into the above equation. X squared becomes rho squared sine phi squared cosine theta squared plus rho squared sine phi squared sine theta squared. This equals 4. From this we can find rho. Here between these two, the common is rho squared sine phi squared. It's rho squared sine phi squared equals to sine squared of phi actually. And what's left here? We have cosine theta squared plus sine theta squared equals 4. Sine squared plus cosine squared is 1. This is 1. That means you get that rho squared sine squared of phi equals 4. And from this, we can say rho squared is 4 over sine phi squared. And from this, we can say rho equals 2 dividing by sine phi. So rho is 2 dividing by sine phi. That means rho is starting from 0 to 2 over sine phi. And sine phi is 1 over cosecant. So rho is 2 cosecant. 2 cosecant of phi. This is rho. That means rho is from 0 to 2 over sine phi. Now I'm going to clean this one. Well, let's leave this. Let's have this one here. And rho belongs to 0 to 2 cosecant of phi. Now we have all the lower and upper limits. To find the volume, in spherical coordinates, we say V equals the triple integral d rho, d phi, and d theta. We have rho squared sine phi. We have rho squared sine phi. This is for the rule. Okay, rho is from 0 to 2 cosecant phi, or 2 over sine phi, and phi is from minus pi over 2 to pi over 2. Minus pi, so it's from pi over 4 to pi over 2. pi over 4 to pi over 2. And theta is from 0 to 2 pi. That's all. This is the triple integration on the spherical coordinate. Now we just try to find the integrations. Okay, we have v equals, we take the first integration with respect to rho. That is the integration from 0 to 2 pi. Integration from pi over 4 to pi over 2. Then the integration of this function with respect to rho is rho cubed over 3 sine phi, because we take the integration with respect to rho. And rho is from 0 to 2 over sine phi, or 2 cosecant phi. It's the same. Say sine equals 1 over cosecant, or here you say cosecant phi equals 1 over sine phi. Now we say we have d phi d theta also. It equals the integration from 0 to 2 pi. Integration from pi over 4 to pi over 2. Then we replace rho by 2 over sine phi. Then we replace by 0. When we replace by 0, it's 0. But when you replace by 2 over sine phi, it becomes 8 over 3 sine phi, but to the power 3, times sine phi minus 0. So we just ignore that part because 0. We have d phi d theta. Now you simplify these two as again of sine phi squared in the denominator. So v is the double integration from 0 to 2 pi, and from 0 to pi, so from pi over 4 to pi over 2. For 8 over 3 sine phi squared d phi d theta. Here we say the derivative, and this equals to 1 over sine squared of phi is cosecant squared of phi. It equals to the double integration from 0 to 2 pi, and from pi over 4 to pi over 2, for 8 over 3 cosecant squared of phi d phi d theta. Okay, for the derivatives, we say the derivative of tan theta, or tan x, let's say tan x, its derivative is 1 over cosine squared of x, and the derivative of cotan x, its derivative is 1 or minus 1. It's minus 1 over sine squared of x. But here we have 1 over sine squared, as we have this equals to minus cosecant squared of x. This is secant squared of x. That means the derivative of cotan is minus cosecant squared of x. That means here we say this integration, the integration of cosecant squared of x dx equals to minus cotan of x, because the derivative of cotan is minus cosecant squared. That means the integration of cosecant squared of phi is minus cotan of phi. It's minus cotan of phi. It equals to integration from 0 to 2 pi, and the integration of the function with respect to phi, it's 8 over 3 times minus cotan of phi, and you can say it's minus 8 over 3 cotan phi. where phi is from pi over 4 to pi over 2. And cotangent is cosine of a sine. It's cosine of a sine. This is d theta. We have on the integration. Now we have this minus 8 over 3. It's integration minus of from 0 to 2 pi, multiplying by cotangent pi over 2 minus cotangent pi over 4. It's cotangent pi over 2 minus cotangent pi over 4. Cotangent pi over 2 is cotangent is cosine phi, cosine pi over 2. It's cosine phi divided by sine phi. And here cosine pi over 2 is 0, dividing by 1, where when phi is pi over 2, it is 0 over 1, which is 0. So this term is 0. And this one, we say if cotangent, if you have cotangent of pi over 4, it is cosine pi over 4 divided by sine pi over 4, which is 1. That's 1, because sine and cosine of pi over 4 are equal. That means this term, the second term is 1. This is 1. That means it's minus 1, since you have this negative sign in front of cosine pi over 4. This is d phi, d theta. And this equals to the integration from 0 to 2 pi. We are going to simplify it more. It becomes minus 8 over 3 times minus 1 d theta. Because this term is 0 and this is 1. So we get minus 8 over 3 times minus 1 d theta. It equals to the integration from 0 to 2 pi for 8 over 3 d theta. Now we take on the integration with respect to theta. The integration of a constant is the constant multiplying by the variable. The variable here is theta. It equals to 8 over 3 theta, where theta is from 0 to 2 pi. When you replace theta by 2 pi, it is 8 times 2 pi over 3 minus. When you replace theta by 0, you get 0. So you ignore this part. It is 16 pi over 3. This is the volume which is bounded by those, the graph of those functions. That's for the first part. So the volume is bounded by this, and that is 16 pi over 3. We now have another example. It says, find the volume of the solid which is bounded by, or which lies outside of the cone. This is a cone, and inside this sphere. Outside of the cone and inside the sphere. Let's first draw the graphs. We say as part B, it says z squared equals x squared plus y squared. Okay, so it's, let me check the equations again. Z squared, yeah, that's correct. And x squared plus y squared plus z squared equals 1. This equation is the graph of double cone. It's the graph of double cone, which is on the z-axis. I'm not going to talk about how to draw the graph of the cone, because we talked about this before in chapter 1. This x, that's y, and this z-axis. It's double cone. That means as for both above and below. This part and this part, sorry. This is the cone. This is the graph of z squared equals x squared plus y squared. And the graph of this sphere, the graph of the sphere, it says its radius is 1. This r squared means r is 1. Yeah, let's say it's 1. The sphere is it's like this. It says the solid is inside of the sphere and outside of the cone. That means here, this and this. Here also we have, because in this side also we have solid because it's sphere, and it's in the sphere we have a cone. This is the graph. This is the graph. Here we have this also. It's like this. It says find the area which is in the outside of the cone and inside of the sphere. Here, this angle is pi over 4, and also this is z-axis. This is z-axis, and this angle is pi over 4 also. That means phi is from here to here. Phi is from there to here. It's from pi over 4 to this angle, and this angle from here to here is pi minus pi over 4. We just subtract this angle from it, which is 3 pi over 4. So this angle is 3 pi over 4. It means phi is from pi over 4. This is pi over 4. Here you have this part of the solid for the volume, and this part also. We just have the solid from this to here. Okay, and it is from pi over 4 to 3 pi over 4, means phi belongs to pi over 4 to 3 pi over 4. And here we have the radius of the circle, of the sphere. The radius of this sphere is 1, means rho belongs to 0 to 1. And here we have the sphere, which is 1 round, okay? And it's from 0 to 2 pi. As you see, the sphere is from here to here. That means theta belongs to 0 to 2 pi. These are the limits. I'm just going to write down the triple integral. We have the triple integral for rho squared sine phi d rho d phi d theta. Rho is from 0 to 1. Phi is pi over 4 to 3 pi over 4. And theta is from 0 to 2 pi. This is the triple integral that we should find the value. And the result of this triple integral is the volume, which is in the outside of the sphere and inside of the cone. Sorry, it's outside of the cone and inside of the sphere. So that's all. And here, just try to find this triple integral. It's just calculations of this triple integral. First, you should need to take the integration with respect to rho, the second one with respect to phi, and the third one with respect to theta, and you'll get the result. That's for yourselves. Okay, and it's enough for today. If you have any question, you can ask. I'll give more explanation